Welcome to Instant Mechanics. Today we are going to solve some questions under simple stress and strain. Subscribe to the channel and share the video. Example 1. A uniform beam weighing 500 Newton is held in a horizontal position by 3 vertical wires, one attached to each end of the beam and one is at the mid-length. The outer wires are brass of the diameter this, and the central wire is made of steel with this diameter. If the beam is rigid and the wires are of the same length and unstressed before the beam is attached, estimate the stresses in the wires. If we have the Young modulus of brass to be 85 and for steel is 200. Let's see how we go by this question. So we can draw the diagram for the bar. So let's assume we have a horizontal bar being held by these 3 wires. So we have wire 1 and wire 2, and this is wire 3, and they are holding this bar in position. So these are the wires, and this is the bar. So wire 1 is made of steel and brass, and wire 2 is made of what? Steel. So this one is a rigid portion. This is brass, steel, and another brass. Since they are made of the same length and they are holding a uniform bar, we can get the elongation produced in each of the wires to be the same to balance this bar. So from the idea of the elongation, we can say that the elongation produced in a brass is the same as the elongation produced in a steel. So we can equate them. Elongation in brass is equal to elongation in steel. But we know that elongation, what's the formula? Is force times the length over area times the Young modulus. So for the brass, we can say the force in the brass times the length over the area in the brass times the Young modulus. And out of the steel, you can find the force in steel times the length, the area of the steel, and the Young modulus of the steel. So we can equate this one in the equation 2. Since the elongation produced is the same, so we can get FBL on the area of EB equal to the force in the steel and the area in the steel E in the steel. They have the same length, but the question said they are made of the same length. So this is the same length. The L can cancel out, leaving FB on AB, EB, FS on AS, ES. Let's bring back our values into the question. We don't know the force in B, so we can maintain it FB over what is the area of B? We have pi on 4. What was the diameter? The diameter of the brass was 0.125 centimeters. I'm converting it to meters. Divide by 100. So it will be 0.00125 pi d square on 4, multiplying the E of the brass, which is 85 giga. So 85 times 10 raised to the power 9 equal to the Fs on the area of the steel, pi d square. What was the diameter of the steel? 0.00125 0.0625. So in meters, 0.00625 square times the E of the steel, which is 200 giga. We have this. After punching all this, I'm going to get FB on 104,310.69 should be equal to FS on 61,359.23. So I can make either one of the F a subject. So making F be the subject, I'm getting 1.699 Fs. We can also get an idea from this that since the wires are holding this bar in equilibrium, then the forces induced in them, the summation of the forces, will hold this bar in equilibrium because it is weighing 500 Newton, and the sum of the forces will keep this bar in equilibrium. Therefore, we can say that this first brass plus this second brass plus the steel is equal to this, the weight of the bar. But look at this, the brass is in two forms. It is 2, so we can say 2 times the force in the brass plus the force in the steel equal to what? 500 newtons. And we know that FB is expressed in terms of Fs here. So 2 times 1.699 Fx plus F of x is equal to 500 newtons. After punching this plus this, you're going to get 4.3998 F of x into 500 Newton. Making F of x the subject, you're going to get a force of 113.64 newtons. And you bring back this force into this equation to calculate for FB, and you find out that FB is also equal to 193.18 Newton. So these are the forces induced in the wires. So for a steel wire, the force is 113.6 Newton, and for a brass, it is 193.18 Newtons. We can calculate the stress in the wires because we have our force. So stress in the brass, which is the force in the brass over the area of the brass, and we have the information. Now the force in the brass is 193.18 newtons over the area of the brass. What is the area of the brass? Pi on 4 d squared. And the diameter of the brass was this, converting to meters square. So I'm getting stress in the brass to be equal to 157.4 megapascal. Now, stress in the steel is the force in the steel over the area of the steel. And I know that the force in the steel was 113.64 newtons over the area. Pi, what is the D? The diameter of the steel, 0.000625 square. So I'm getting stress in the steel to be 370.4 megapascal. So there's going to be more stress in the steel than in the brass. This is the answer for question 1. Question 2. A uniform steel rope of this length hangs down a shaft. Find the elongation of the first 125 meters at the top if the density is this and Young modulus is that. So this question, the steel rope is hanging down on a shaft and its weight is acting downwards. So we should find the elongation produced in the first 125 meters, which is half of the entire length. So we are going to find the stress or the elongation produced in half of the rope. So we can get the diagram like this. Let's assume the rope is hanging down a shaft. So we assume this is the rope, fixed end. It is acting down on its weight. So this, what we have to do, since it is being acted upon by gravity, we cannot estimate the elongation just like that. And we have to take a small portion of it, then we integrate to get the entire elongation. So I'll take a small portion and I'll call it dy, the differential portion. So this is the entire length, which is what? L. I'll call this one dy, but I have it to be the width to be y and the height to be dy, and I can integrate. You understand? So we have the total width, we have the total length to be L, and we are going to consider, so considering just a strip, this small portion y and the height dy, we can say that elongation produced is equal to density over Young modulus times the y dy. If you play with the formula for elongation, you're going to get the density over the Young modulus times this height. So we are going to differentiate or integrate with respect to y. That's why I brought the dy. So I can integrate with respect to y. So the integral of the elongation and the integral of the density E with respect to y dy. Since I want the elongation in half, the first 125, which is half of the bar, I can integrate from half, which is L on 2, to the other top. So I'll start integration from half of it, which is L on 2, to the total length L, because if it here is 0, here will be what? L to that. So playing with the integration here with respect to y is going to come out with, because we have limit, 3 on 8 density on E L squared. This is what you're going to get after playing with the integration. So check your integration and we can bring back the values in it. We have our density in the question to be 7,840. We have our E to be 200 by 9. And we have our L to be 250 meters. This is kilogram per meter cube. And this is Newton meter square. So the elongation produced is 3 on 8 by density, which is 7,840 on the E 200 giga times L squared. The L, the length was 250 squared. I'm getting the elongation produced in half of it to be 9.18 times 10 negative 4 meters. You can convert your answer to millimeters. That's it. This is hanging, a bar hanging. It has a different approach of calculating the elongation and the stresses as compared to a bar being loaded easier. So let's move to the next question. Steel bar having a rectangular cross section, this by that carries an easier tensile load of 180 kilonewton. Estimate the decrease in the length of the size of the cross section if the Young modulus given is that and Poisson's ratio V is that. So solution, it is a rectangular what bar. So we know that the width, something like this will be what the length, and this is the height. So we can know that the length was given as 7.5 centimeters. We can convert it to what meters. The height is 2.5 centimeters. We have our load, our force with 180 what kilonewtons. The E to be 200 gig. We have Poisson's ratio V 0.3. Okay, so I can calculate my area since area of what a rectangle, length times what height. I can calculate my area in terms of meters. So 7.5 centimeters, I'm converting to meters, divide by 100 times 2.5 divided by 100. So my area is going to give me, I'm having 1.875 times 10 raised to the power negative 3 meters for the area. Are we good? Okay, now we have the area, we have our force. What can we do? We can calculate the stress induced in the bar. Remember, we are going to find the decrease in length. That is what change in L. We are going to find. But we have to know the stress before. This question contains a lot. We have to know the stress in the bar. So stress in the bar is the force 180 kilo divided by the area 1.875 10 negative 3. So the stress in the bar is giving me 96 megapascal. This is the stress. But from Hooke's law, we know that strain is stress over E. There we go. So we can calculate the strain too. Now the stress is 96 mega and the E is 200 giga. Therefore, the strain produced will be 4.8 times 10 raised to the power negative 4. This is the strain. Are we good? And we know that this strain is an axial strain. Axial strain. This strain is an axial strain, which is strain in the x direction. And Poisson's ratio can link axial strain and lateral strain, which is V is equal to the lateral strain over the axial strain. Remember, when this bar was in tensile load, tensile, there's going to be an increase in the x direction, but there's going to be a decrease in the y direction. So we have Poisson's ratio, we have the axial strain produced, so we can calculate for the lateral strain. Are we good? So our lateral strain can be Poisson's ratio 0.3 multiplying this, the axial strain. Therefore, our lateral strain is giving us 1.44 times 10 raised to the power negative 4. And then again, we know that anytime you have a lateral strain, it is given as either change in diameter over diameter, or change in height, or change in length over length, or change in width over the width. So now we are finding change in what? The length. So we can say that the axial, the lateral strain, is change in length over L. And now we want change in L. We have our L and the lateral strain. So I want to leave my answer in centimeters. So I have this, I just calculated for it. 1.44 times 10 raised to the power negative 4 times the length. What is the length? 7.5 centimeters. Therefore, my change in length, or my decrease in length, was 1.08 times 10 negative 3 centimeters. This is the decrease in length of this bar. Let's move to the next question. A metal rod of diameter 1 centimeter is loaded in tension. When the tensile load is 5 kilonewton, the extension of 25 centimeter length is measured accurately and found to be 0.0 centimeters. Estimate the value of the modulus, that's E, of the metal. So from the question, an extension was measured to be that. This is the extension. So we can list our parameters. Solution. What do we have? We have our elongation produced. That was 0.0227 centimeters. We have a diameter of 1 centimeter, and we have a force of 5 kilonewtons, and the length was given. The extension of this length, 25 centimeter length, was this. So the length was 25 centimeters. But we want to find what? E. Looking at the parameters, there is a link between them. E. Elongation can be P L on what? A E. There we go. We have elongation, we have force, we have length. We can calculate the area. Then we can make E the subject from this. So E can be the force over that A and the elongation produced. We have all this. Let's try to manipulate it and see. So our E is equal to, what is the force? 5,000. The length. The length is 25. If I want to send it to what? Meters, divide by 100, which is 0.25, over the area. The area pi d square on 4. What is the d? This is 2 meters, will be 0.01. 0.01 square. So this is the area pi d square on 4 times the elongation produced. And the elongation, sending this to meters divided by 100, we are going to get 2.27 times 10 raised to the power negative 4. And my E is going to give me 70.1 gigapascal. Approximately, you can say E is 70 gigapascal. So that's it for question 4. Very simple. The steel wire working a signal is 750 meter long and 0.5 centimeter diameter. We should assume a pull on the wire is 1.5 kilonewton. Find the movement which must be given to the signal bus end. If the movement at the signal end is to be that, then we should take Young's modulus to be 200 giganewton. So our parameters can be listed here as, what is the length of the wire? We have the length of the wire to be 750 what meters long, and diameter 2 meters, 5 times 10 to the power meters. And we have the force given to be what? 1.5 kilonewtons. We have the E to be 200 giga. Now we have diameter. We can calculate some area here. So if I'm to calculate the area, I'm going to get pi d. What is the d? The diameter. Pi d squared on 4. And I'm getting my area to be 1.9634 times 10 raised to the power negative 5 meter squared. Are we good? So they want to know the movement, find the movement which must be given, meaning the bar is fixed and we need some movement, and the movement can either be an elongation or a decrease in what? In length. So if we are trying to find a movement, then something is saying about the elongation produced. So let's find the elongation produced when this force was acting or pulling. You see, assume a pull, there was a pull on the wire. So let's look at the elongation produced by this force. So the elongation is the force, the length, the area, and the E. Therefore, our elongation can be the force. What was the length of the bar? We have 750. The area, we have our area to be 1.9, and the E to be what? 200. Therefore, the elongation produced was 0.28649 meters. Are we good? So if the force produced this elongation, and look at the question, you're saying if the movement at the signal end is to be 17.5 centimeters. So the bar or the wire itself is moving 17.5 centimeters at the end of the what? The signal. And this force is also producing this amount of what? Elongation or movement. Then the total movement at the end of the signal wire can be the one it is moving with plus the one the force is producing. So movement to be given, the movement to be given to the signal box end is equal to the elongation produced plus the movement at the end of the signal, which is going to give me this one produced by the force plus the already produced one, 17.5 centimeters, which is 0.175 meters. Remember, this is meters, so I have to work in meters. So at the end, the total movement produced will be 0.46149 meters, or 461.49 millimeters, and we are good to go. Example 6. Check the question and the answer very well. A circular bar of diameter, this is subjected to an axial tension of that. If the material is elastic with the Young modulus to be 70 gigapascal, we should estimate the percentage elongation. The percentage elongation. All right, so we have our solution. I was given a diameter of what? That. So in meters divided by 100, which is going to give me 0.025 meters. I have my force to be 20 watts kilonewtons. So if I have diameter, then I can find my area. Anytime I know there's a diameter, then something related to area is coming. So pi d square on 4. So my area is now going to give me 4.908 times 10 negative 4. To find percentage elongation, and we know that the strain produced, we should first find the strain produced in the material. But how can we link strain? We know that from Poisson's ratio, strain is giving us the stress over what? Young modulus. But stress is force on area. So combining them, you're going to get the force over the area times the E will give you the strain produced. We good? Alright. So our strain will be the force, which is 20 kilo over the area, 4.908, in the E, 70 giga. Therefore, our strain produced was 5.82 times 10 raised to the power negative. This is the strain produced. People will ask, why don't we calculate the elongation? Elongation is PL on what? AE. Do we have the length? No. We have the force, we have the area, we have the power. We don't have any length. Therefore, the strain produced, strain is the deformation produced. And the deformation can be assumed to be what? Either an elongation, because if the bar elongates, that strain, that deformation produced can be what? Elongating, or what? Compression. Meaning, if you don't have the length, the strain can be assumed the deformation produced was either elongating. Are we good? So we have the strain produced as this, and we want to find the percentage of the elongation here, which is the strain. So the strain percentage can be this multiplied by what? 100%, which is going to give me 0.0582%. So the percentage elongation, therefore, the percentage elongation is given as 0.0582%. Thank you for watching the video. Subscribe to the channel. Bye.